So yesterday we covered the basics, right? We covered sig figs, how to know when to round and what place to round to, just because we're going to use those skills all the time going forward. So we kind of needed it to build off of. And today we're kind of getting more into the chemistry of things. So if we take a look at this next slide, we'll be covering like general atomic theory, like Dalton's atomic theory, the periodic table. So that means like how to read it, like what's a group, what's a row, and like why is it organized the way that it is. And then we'll also get into how to write, read, and balance chemical equations. And then that leads into stoichiometry, which is like arguably one of the most important things that you'll need to know going forward. So that's why we've got it early on. All right. So starting off, we're not going to go too far deep into atoms just because, 1 hour class and we only have 9 of these. But the basic thing that you'll need to know is that, like I'm sure you've heard, the atom is basically made up of two separate regions, right? So you've got the nucleus, which has your protons and neutrons, and then it's the nearly completely empty space around it, which is where the electrons kind of hang out. So if you need like help visualizing stuff like this diagram has, the protons and neutrons are much bigger and much more massive than your electrons. So even though there are a lot of electrons floating around in that empty space around the nucleus, they're so small that they really don't contribute that much mass. So when you think about the fact, like you might have heard that carbon 12, or like it has a mass of 12 AMU, right? Atomic mass units. Basically, all of that mass is coming from its protons and neutrons, which are in the nucleus. The electrons weigh almost nothing, if you want to think about it that way. And then this diagram shows that the electrons are kind of, I guess, split into energy levels, or like, yeah, energy levels, we like to call them. It's not that they're super organized like this, because electrons are just like floating around, going from place to place. If you think about it, it's kind of like how a gas particle will just like go around the room, hitting the edges and like just bouncing around, but still staying within that room. That's kind of how electrons behave. They're not necessarily confined to, I guess, like being a certain distance away from the nucleus. It's just that they're everywhere and you can't really locate an electron. It's just more about knowing the probability of like generally where it's going to be. Like you can figure that it's going to be likely that it's in this region, not likely that it's in some other region. And obviously you can see from the plus and minus signs and the blank green ones that protons have a positive charge. So one proton has a +1 charge. Electrons have a negative charge, -1. And then neutrons have no charge. And without going further into that, that's basically all we need to know about atoms. And that kind of leads directly into the periodic table. So we were talking about protons, electrons, and neutrons before, and a lot of that can be applied here. So if we just circle in on like, 1 second, let me check the chat. Okay, never mind, everything's taken care of. Yeah, so if we just choose like an element to look at here, just for an example, let's look at boron. So I'll draw a better circle. We see at the top that it has a big 5, right? And if we count, like we can see why, obviously going left to right, top to bottom, we see 1, 2, 3, 4, 5. And this 5 is called boron's atomic number. And basically how you want to think about it is that this is what makes boron boron. It has 5 protons. And that's what the atomic number means, the number of protons that a certain element has, and that's what makes one element different from another. It's the amount of protons that it has. But if we also like try to use some logic, we're talking about elements that have a charge of 0, right? Like they're electronically neutral. So that means for every proton you have, you need an electron to balance out the charge. So if you find boron in just like an uncharged state, then you're going to have 5 protons and 5 electrons, just because you need to end up having a neutral charge. And depending on what isotope of boron you have, you're going to have a different amount of neutrons. So Boron 10 and boron 11, for example, they're still both boron, right? That's why they have boron in the name. But the difference is that boron 10 is going to have 10 minus 5, which is 5 neutrons. And then boron 11 is going to have 11 minus 5, which is 6 neutrons. So that's how you differentiate between isotopes. They'll have the same number of protons, which makes them the same element, but they have a different number of neutrons. So they can have kind of slightly different chemical properties. So B is just like the symbol for boron. It's just because like I said a lot last time, people are lazy, so they want to like not waste as much time as possible. So if you put B, everybody knows you're talking about boron, and you don't have to write the other 4 letters out. 10.81 is what you would consider the atomic mass of boron. So the way you can think about it is either we'll get into what a mole means later on, but you can think of it as a mole of boron weighing out as 10.81 grams, or you can also think about it as one atom of boron having a mass of 10.81 AMUs, or so AMU means atomic mass unit, but that unit's like kind of old. So I think like chemists are switching to like Daltons now, but AMUs, Daltons, and U, which is kind of just like unit, all mean the same thing. Yeah, so basically the reason it's not like 10 or 11 is because 10.81 is an average. So it's basically telling us that like boron 11 is like a lot more common than boron 10. Yeah, what's up? You can unmute yourself if you have a question since you raised your hand.
Okay, so since the protons in an atom all have a positive charge and the same charge and like opposite charges attract and the same charge will cause two things to fly apart, what keeps the protons in the nucleus from flying apart and what keeps the electrons from colliding with the nucleus?
So basically, I don't know if you've ever seen like an energy diagram, but I don't know how to exactly draw it, but like it kind of looks like this. I'll explain what that means. Basically, like this is potential energy, and this is the electron's distance from the nucleus. I'll just write distance. And so basically, you can see how at the lowest potential energy, that's what you would consider like most stable, and it would want to be at its most stable point at all times. Basically, you can see if the electron is on top of the nucleus, which would be 0 distance, so it's right here, it's at higher potential energy than it wants to be. So it actually wants to go out to a further distance, and that's because basically you have different energy levels, right? So if I go back to the last slide, it kind of like illustrates how there are energy levels within the atom. We can get more into like structure in a different lesson though, because I definitely want to keep this more on chemical reactions. But if we see how like there's one ring of electrons around the nucleus here, and then there's another like separate ring, it's not, okay, that was a really bad drawing. So like I'm talking about this ring and this ring. Basically, without getting into it too much, in your first ring, you want to have only 2 electrons there because like that's kind of like the maximum you can have in the first energy level. And then if you start like trying to shove more electrons in, they start, it's called shielding each other. So basically the negative charges come way too close to each other. And like you said, they're going to start repelling each other and making the other electrons want to move out further, which is why you would need to start another energy level. So every energy level after this first one, you can fit 8 electrons, but after that, they start repelling each other way too much, and that's why you need to move out further. And then for the nucleus, the reason that like the electrons on the outside don't like pull apart the nucleus is because there's nuclear strong force holding the protons and neutrons together, and it's actually like, I don't know if you've heard of like the fundamental forces before, but it's like one of the 4 fundamental forces. I think you learn more about that in like physics. One of them is like gravity, I think. So that's an example. But yeah, so it's called a nuclear strong force that's holding the particles of the nucleus together, which is stronger than the attractions with the electrons, which is why stuff doesn't just go like flying everywhere. But yeah, I can definitely, if you're still curious, like I can definitely go into it further just by email or something. Yeah, what's up?
Excuse me.
Mm-hmm.
If you go back to the previous slide, I want to ask you a question. How can the protons, why do they stick together? Because positive and positive repel each other.
Yeah, so nuclear strong force is a really interesting concept. Honestly, it's more physics than chemistry, right? So it's not really covered in chemistry, but I encourage you to like search it up after class or even right now if you want to. I'm just not like an expert in it, so I don't think I could give you as great of an explanation as like Wikipedia, but definitely search up nuclear strong force after class if that's something you're interested in.
Okay. Okay.
Also, if you guys have any questions and you don't want to speak up in class, feel free to put them in the chat and I can answer them to the best of my ability.
All right, so now that we have like a general idea of, I guess, the small scale, which is like atoms, we can move on to kind of like the mathematical basis of chemistry, which is the equations, right? So this is basically how you express a moment in time, if you want to think of it that way. Like if we look at this first one for a second, what I'm trying to say with this equation is that this is butane. You don't have to know that, but like that's butane. This is oxygen gas. This is carbon dioxide gas, and this is water. You might think it's a liquid, but it's actually in gaseous form here, even though it doesn't say it. But basically what I'm trying to say with this equation is that butane and oxygen are reacting. This kind of reaction is called combustion because you're reacting with oxygen gas, and they're producing carbon dioxide and water, both in gaseous form. And basically like the terminology surrounding chemical equations is that what you have on the left or like behind this flat side of the arrow are the reactants. So the thinking behind this terminology is like these are the things that are reacting together, right? So that's how you can remember it. And then what you have like after the head part of the arrow is or are the products if you have more than one. Also, you don't need to have more than one reactant. It's just that this is the kind of reaction that we have here. So if you have more than one product on the right side, then you would have products. And in this case, those would be carbon dioxide and water, both in gas form. So like those are the, I guess, two big terms you would need to know for chemical equations. And you also see that you have these numbers next to each species, right? So those are your coefficients. Kind of just a math term. You've probably heard it if you've taken like algebra 1 or something, or even like pre-algebra. Because like if you have like 4x, 4 is the coefficient for x, right? So it's the same idea here. The reason that these exist is because as chemists, you kind of want to know like if you add x amount of stuff, you want to know like, am I going to produce y amount of this other thing? Like you want to be able to predict so that say you're in a lab, you want to know how much you're making, just in case you might not have enough for this certain next step you're going to go towards, or if you're going to produce like way too much and you need to know like, do I need to store stuff afterwards? So if we take a look at a different type of chemical reaction, this one you can see, I guess, two clear differences, maybe like three. So first of all, we have these shortened, I guess, like phrases in parentheses, and they're kind of in the subscript, which means that they're like underneath the bulk of the text. So what this means, AQ in parentheses means aqueous. So what you want to think of for aqueous is like if you put salt in water and you like mix it around, eventually like you're not going to be able to see the salt, right? And that's because it's dissolved and dissociated into the water. And aqueous basically just means you made an aqueous solution with whatever it's describing. So in this case, this is called phosphoric acid. And it just means that you have some phosphoric acid in water and nothing solid, basically, which is why you would put AQ. L, on the other hand, obviously this is water, but there's nothing dissolved in here. L means it's a pure liquid. So unlike before where we put something into water, like stirred it and made a solution, L is just the water. Or if you're thinking of some other sort of compound, it could be like just liquid ammonia, but nothing else inside of it. So that's why you would put L, because L means it's the pure form of that liquid. I'm trying to think of some other examples. If you've ever heard of like ethanol or methanol, those are also some pure liquids that you might come across in chemistry. And here we have AQ and AQ again. If you're talking about solids, you would use parentheses S. And if you're talking about gases, you would use parentheses G. One other clear difference from the equation at the top is that you have this double arrow here. It looks a little different because this is just like a screenshot of an image I took, but usually like when you're handwriting, you would do this. So like you can see how you leave out half of the arrowhead for each of them. And this basically means that the reaction is reversible. So in this case, we have a one directional arrow. So that means, I guess like in easiest terms, this reaction is only going to go this way. There's no chance of getting it to go to the left. But if you have this double arrow, for example, depending on how you manipulate what kind of environment the reaction's in, which we might talk about like later in this course, but definitely not now. Depending on what environment you put the reaction in, you can force it to go right or left, but it can definitely go either way. And yeah, so for superscripts and subscripts, you see superscripts here. The only things that you'll ever see in superscripts are some sort of description about the charge of the compound. So in here, just a single minus sign means that this has a -1 charge. So -1 and minus mean the same thing. And then a single plus sign means a +1 charge for this specific thing. If you see like 2+, that means a +2 charge. It's usually not written like +2. So like, for example, if I had HPO4 2-, you would want to write it as 2-, even though like you would think of it as a -2 or a -2 charge. Sorry, I just got to your question. Burning butane releases energy, so if it were possible to undo that, you need to input energy. Yeah, exactly. Generally though, combustion reactions, it's like kind of impossible to undo them, right? Because if you think about it, you're like burning something. How do you unburn something, you know? All right, yeah, so we can move on to the next slide. All right, so this is about writing chemical equations. I just showed you like the general makeup of them, right? So on the left, you'll have your reactants. In the middle, you've got some type of arrow, depending on what type of reaction it is. We'll only use like single head arrows going to the right today, just to make things easier. And then on the right, you'll have your products if you have more than one. So the first step is definitely you need to have a general familiarity with what kind of compounds are common in chemistry. So I hope we all know that water is H2O, carbon dioxide, CO2. What less of us might know is that some elements come in dimolecular forms naturally. So dimolecular, if we break that word apart, it means 2 per 1 molecule. So in that case, this would mean that in nature, like the oxygen gas that you breathe is found as O2. Yeah, so those are some common things you might come across. Another thing is like methane, CH4. That's usually found as a gas. Here, I'll just like write methane next to it so you can put that to memory a little bit, I guess. But besides those, there isn't really anything you should like really know or have memorized anymore. I guess there's like nitrogen gas, which is similar to O2 in that it's dimolecular naturally. Okay, so your second step would be to have your reactants and products on the correct side. Obviously, this is important. So usually if you're like taking a quiz, yeah, O3, ozone, is allotrope. So allotrope basically means like it's a way that you could find the element in nature, but it's just not as common. Yeah. Oops, what did I just do? All right, there we go. Yeah, so you need to have your reactants and products on the correct side. That just means that like before you start putting anything to paper, you really need to know like what is my goal here? What am I reacting? So 3, I just put some like very basic niche reaction types here. So like we saw before with the, so we saw this before. I'm not gonna balance it right now, but like we had this, right? On a previous slide. This is a type of combustion reaction, and because there's the O2 there, obviously. And it's called a hydrocarbon combustion because this compound that we're reacting with the O2 only has C and H in it. So hydrocarbon, once again, if we're like breaking the word apart, hydro means like the hydrogen part, carbon, obviously carbon. So whenever you have a hydrocarbon reacting with oxygen gas, you're only going to produce CO2 and H2O, and these are both going to be in gaseous form. The reason for that being you inputted so much energy that it just goes through a phase change and goes from liquid to gas in the case of water. For an acid-base neutralization, we've probably all seen this in like some sort of science class before. Like if you take a baking soda and like hydrochloric acid, for instance, or I guess instead of hydrochloric acid, say like vinegar, since that's probably more comfortable for us. If you react those two, you're gonna see like not bubbling, but like you would see nothing actually because it's an acid-base neutralization. But if you had like some sort of indicator in there, you would see a color change. And basically what's happening there is that it's a double replacement reaction. It's just a special kind. And so the H from the acid and the OH from the base becomes water. And then the rest of the stuff rearranges into a salt. And a salt just, it's a very broad definition. It basically just means like you have a cation and an anion that formed from an acid-base neutralization. And the other types of replacement reactions we'll just like cover as we come across them. All right, so I think what I'll do for this is, let's see, if anybody's comfortable with the annotation option, definitely go ahead and give it a shot while we're all together like this. So we'll do number 1 all together, and then we'll go into breakout rooms for number 2. All right, so here. Yeah, so I'll be writing, but feel free to like jump in if you want. So, oh yeah, there we go. Go ahead. We were talking about like how we needed to have some, oh, okay, wait, hold on. Make sure to work together, guys. So if you see somebody writing something down, try to work on a different part. Yeah. Yeah, so methane is combusted to yield water and carbon dioxide. So like we said, combustion, if you hear that word, it should mean something to you. And that means that, like we have here, there's O2 gas involved. And right now, don't worry about balancing anything, guys, just in case you were. I don't know if you were. We're just writing, making sure that our reactants and products are in the proper places. But yeah, so here methane and combust tell us that our reactants are going to be methane. Like I said before, methane is CH4. It's okay if you don't have that memorized right now. And combust, O2, to yield. In other words, yield means like form or produce. So they yield water and carbon dioxide, and looks like we took care of that. Nice. And then for number 2, we have hydrochloric acid. These might be a little bit unfamiliar for us, so I'll make sure to help us out. Neutralizes sodium hydroxide. Yeah, whoever wrote in orange has the correct idea. Hydroxide is OH minus. So when you have, oh yeah, nice. Whoever typed it out, nice job too. Yeah, so sodium hydroxide would be NaOH. Once again, it's okay if you don't know that. Yeah, so nice. We just covered how like a hydrocarbon combustion will produce water and CO2. And then an acid-base neutralization is basically a double replacement reaction. What's going to happen is that the H from the acid, and I'll just write this. Okay, never mind. Yeah, go ahead and write the OH in. I'll just like do this to the 3. The H and the OH contribute to forming the H2O. So if you like add those up, you can see that there's 2 H's and 1 O. And then in this case, the Na plus and the Cl minus are going to make NaCl. So nice job there, guys. And yeah, we'll move right on.
What does it mean by neutralized?
I guess if you think about it, you would say neutralized because like say you started with acid And we're just thinking about like acid in a beaker, or a beaker is like a cup, if you didn't know. So say you have acid in a beaker and you take the pH of it. We know that like the pH of acid are really low, right? Like they're close to 1, 2, 3. Why we call it neutralized is if you like pour in the base, the pH starts going up, and it if you add like the correct amount, it starts settling around 7, which is a neutral pH. So that's like the reasoning why it's called neutralization. It's because you want to bring the end pH close to like 7, so you know that the reaction's finished. All right.
Okay.
All right, so we just wrote chemical equations, but now we got to try and balance them, right? So obviously, I have some practice lined up for the next slides. So the steps, we're pretty much doing the same thing. So we read like the words and we try to discern like what are the reactants here and what are the products. And then what we have to do afterwards is we just got to make sure that the atoms of one element adds up. You're familiar with that? Yeah, that does happen. Yeah. It's just that that would be sodium bicarbonate, right? Or you could also call it sodium hydrogen carbonate, which is baking soda. Yeah. But I'm sure you already knew that stuff. Yeah, so the steps in this one are you write the reaction out just like we did, but then we just have to mathematically balance the equation. So that means like if I have, say we're working with like chlorine. If I have 2 chlorines on the left side, I need to make sure that I have 2 chlorines on the right side. But say I have like in the moment 2 chlorines on the left and 3 chlorines on the right. What I can try doing is putting 6 on both sides because that's the least common multiple of 2 and 3, right? So basically like you have to do some, I guess, mental math with least common multiples in order to properly balance. But this is a familiar one just because like I didn't want us to spend too much time here. So I'll just write this out again since we already wrote this for the previous example. Combusted, and I'm just putting the states here too because like it is like more accepted, I guess. Plus H2O. So that's what's happening, right? But from here, we need to basically make sure the amount of atoms of each type on both sides are matching up. So if we look at carbon, can somebody tell me in the chat how many carbons we have on each side and if it's already balanced or not?
There's one on each side and it's balanced.
Yeah, nice. Thanks everybody who said that. Yeah, so we looked at carbon and it's balanced. So we don't need to do anything about the carbons. But let's look at hydrogen for a second. Oh, what's happening with hydrogen? Is it balanced or not? And why is it not balanced? Like, can you tell me what the numbers on each side are?
So there are 4 hydrogen on like one side and 2 hydrogen on the other, so it's not balanced.
Yeah, we have 4 on the left and 2 on the right. So how we balance 2 and 4 is we just multiply the side with 2 by 2, right? So that's what this coefficient does. And if we like distribute the coefficient, we see that 2 times 2 gets us 4 hydrogens, and that matches up with the hydrogens on this side. But the problem is that we need to make sure that the oxygens are balanced. And as of this moment, are the oxygens balanced?
No.
All right, so what should we do to make them balance?
Add 1 more oxygen molecule reactant.
All right, yeah. So basically, I'll just like count up so it's easier to see again. If we distribute over here, the 2 waters on the product side are contributing 2 oxygens. And then the CO2, there's only 1 CO2, is also contributing 2 oxygens. So we have 4 on this side, and we only have 1 O2 on this side. So we have 2. But if we multiply the 2 oxygens in O2 by 2, then that gets us 4. So that's how you would balance this, I mean, pretty simple reaction. I think I actually might have more practice lined up since I titled this slide walkthrough. Let's see. Okay, all right. Here, I want to try some breakout room stuff. Ria, do you have access to that? I don't, again.
No, it's not on mine. I think you should have it because you're the host.
Okay, maybe it's under more. Oh yeah, there it is. All right, so first, actually, could you send the, what is it, the presentation link so that they could do this?
Oh yeah, I can just post it on the classroom right now.
All right, thanks.
Give me like 2 minutes.
Yeah. So this is a combustion reaction again. So hopefully you've like caught on to what that means. I'll just give a hint. Butane is C4H10. And once you have the presentation link, I'm going to set up breakout rooms just so here. Assign. Oops, I got to choose mouse. Okay, let participants choose. I'm going to set up here. How about 6 breakout rooms? And you can choose, don't go in yet, but here, I'm gonna do this. How about if your last name starts with A through D, go into room 1. If it's E through I, go into room 2. J through M, go into room 3. N through Q, go into room 4. R through U, go into room 5, and anybody else go into room 6. So that was for the first letter of your last name. All right, yeah. So make sure you have the presentation pulled up on your own though, just so that you know, you have the screen to be working on and annotating with whoever you're in a group with. All right, wait, does anybody have access yet? Like to
No.
the breakout rooms? Okay,
No.
I'll open it now. All right, if you need me to repeat like the last names, I guess ask me to, and I'll try to remember.
Okay, the presentation's also up, so you guys can access it on the classroom.
You should be in room 6, but you can't do it. Okay, I'll try to assign you. I think you're in room 5, actually.
I can't join room 3 for some reason.
I'll cover that for you. I think you're room 3. I might have to ask Dev to move to another room. Okay. Hey, go ahead and join room 4, just so you know you have other
Okay.
people to work with. Yeah.
Good thing.
Hey guys, how's it going?
I think I got it.
Oh, all right. What's up? What'd you get?
I got 2C4H10 plus 13O2, and then the arrow, and 8CO2 plus 10H2O.
Yeah, nice. That sounds right off the top of my head. Nice job. All right. Since it seems like you guys are finished, make sure you come back. Hey, how are we doing in here?
We actually just finished balancing out the equation.
Oh, cool. What'd you
Hey.
get?
Wait, let me open it up since
We got 2 butane molecules, 13 oxygen molecules, and that's transformed into 10 water molecules and 8 carbon dioxide molecules.
Yeah, that's right. Nice job.
Okay.
All right. You guys can come back anytime since you're done. All right. See you.
okay.
Do you guys like chemistry?
Yeah.
What grade are you guys? What grade?
6th.
Yeah, we've got a lot of 6th, 7th, 8th graders in here.
I'm only 5th grade.
Oh, nice. Oops. All right, seems like we're getting nearly everybody back. Yeah, that should be everyone. All right, so I'll show the previous slide. So basically, I'll also like show this, I guess. You should have had like 2 butane, 13 O2. Wait, hold on. Yeah, 8 CO2 and 10 water. So hopefully you got that. Don't worry if you didn't though. We're all getting there. And it seemed like a lot of people did though, based on the breakout rooms that I went to. So nice job. Yeah, nice in the chat. All right, so now we know how to write and balance and like make sense of it. So how do we actually apply them? And that's where stoichiometry comes in. It basically has like a really convoluted name, right? But it's not, I was about to say not that hard. That's not necessarily true, but it's not like as snobbish as it sounds. So basically what stoichiometry means is that you're just relating the amounts of substances. So if I put that into like planar terms, if I put X amount of, say I'm burning like X amount of butane, like we were just talking about, and I have unlimited oxygen gas, how much water and how much carbon dioxide is going to be produced? That's what like stoichiometry deals with. And it's based around the fact that a mole, yeah, kind of a funny word, but a mole is kind of like the universal unit for amount. So we used to think of like grams as amount, right? Because it deals with mass, but actually like say like 20 grams of water is actually a different amount of water in terms of moles than it is for carbon dioxide. So 20 grams of water is not like chemically equivalent to 20 grams of carbon dioxide in terms of how much you can extract from it, how much you can react before you use up all of it in a reaction. So the definition of a mole is 6.022 times 10 to the 23rd things, for lack of a better word. So if anybody has a calculator, if Sally has 0.0223 moles of apples, how many apples does she have? This is just for us to get used to the fact that we're counting in a different unit than we're used to. It's kind of a lot of apples, so don't be scared by the fact that you get a huge number. And if anybody gets an answer, you can write it in the chat. It's just like a one-step multiplication. I'll write it out too. So what I'm showing here is not like necessarily how you would do it because it's like such a simple calculation, but this is called dimensional analysis, where basically like you set up the units that you're dealing with as, I guess, kind of like numbers so that you can cancel them out visually. So this comes out to, if we're doing sig fig practice here, how many sig figs should my answer have? Say in the chat. 3. Yeah, nice. Yeah, you took a long time writing that out, huh? But yeah, you are right in that it's that many apples. But since we're dealing with chemistry here, we're going to go like kind of sig fig z and scientific notation. So we have 1.34 times 10 to the 22nd apples. So that's kind of how you would deal with moles and like molar mass, but we'll get into that. Yeah, we might not
I have
get.
a question.
Yeah, what's up?
So like the equation that you wrote before, why do you put like the equation on top and like one more on the bottom?
It's basically like, you know how for speed for cars, we talk in terms of miles per hour. So if I'm driving at like 60 miles per hour, that means for 1 hour of driving, I go 60 miles. It's basically like that. What I was saying is that for 1 mole of apples, there's actually 6.022 times 10 to the 23rd apples. So it's kind of like a fraction.
But like, why can't you just like write the equation and like have the answer?
You know, really, there is no right way to write in a write like multiplication out. It's just whatever works for you. So if you wrote it a different way and you still got to the same answer, good job. It's still fine.
Okay.
Okay. So you can see that the title is like underlined here, which means like I linked it to the periodic table website that I use, and the screenshot's also from there, and we also like saw it on like slide 3 or something. But we need to cover like atomic mass and molar mass before we get too far. Yeah, it's a lot of apples. But basically, it's like how I was talking about when I was explaining the periodic table. Here we see the number 14.007 underneath nitrogen. So for nitrogen, that means for 1 mole of N, not N2 in this case, just N, because we're dealing with the element and not how it's found in nature. For 1 mole of it, which is 6.022 times 10 to the 23rd atoms of N, the mass will be 14.007 grams. That's how you can think of molar mass. So this is based on the standard that, like this isn't how it's exactly expressed, but basically 1 mole of carbon-12, which is the type of carbon that has 6 protons and 6 neutrons, will have a mass of 12 grams. Exactly. And like I said earlier, protons and neutrons are where you get the vast majority of your mass. Electrons basically don't contribute any mass at all. So I'm going to do the top example, just because we haven't really done molar mass yet. 1 second, I'm going to go to P table, just so I can show how the website works. So if I go to P table, we're working with PbO2. That's the example I'm doing right now. So here, I don't know if you can see my mouse, but like it's highlighted 82 Pb. We can see that the atomic mass for lead is 207.2. And basically the unit for that would be grams per mole. And oxygen, I mean, that's pretty common, so I just haven't memorized, so I'll show. We have PbO2 contributing 207.2 grams per mole. I hope I remembered that right. And then we have 2 oxygens, so I'm just going to write a 2 as a coefficient, contributing 16.00 grams per mole. It's actually 15.999 if you look at that periodic table, but for a lot of other ones, you're just going to have 16.00. So what you'll end up having is 207.2 plus 32.00. Obviously, the end result is going to be in grams per mole. So what should my answer be applying sig figs? Can anybody tell me in the chat? $239.2. Yeah, in this case, you would want to go to the tens place because between 207.2 and 32.00, the less accurate one is 207.2, right? And that goes to the tens place. So you want your answer to go to the tens place. Whoops. Yeah, so 239.2 grams per mole. I don't really think we have time for that much practice. So here, let's do the same breakout rooms, right? So I'll open them up all again. Go to the same one you went to last time and just do the second, do the second example on here. And before you go into the breakout rooms, just know that this parentheses I have, this is another way that it's also written, but you don't have to look at it, or like basically only look at one of them, right? Because they're the same compound. I just wrote them two different ways just in case you were used to one way.
I think we're gonna have to do stoichiometry for next time.
Yeah, I'm thinking of like instead of like a Google form this time, maybe we just have them, or I guess it could still be a Google form, but we just have them try the last couple of slides themselves. And then
Okay,
at the
yeah.
beginning of the next lesson, I'll just like cover them.
Yeah,
as
that
review.
works.
Yeah. So we don't have to make like additional materials, I guess.
I could try to find like a good YouTube video for it and then post it with the Google form.
Oh yeah, that's true. That's good.
Mhm.
I'll just
Hey, what's up? How are we doing?
Um, so basically we're almost like done with it. So this is 4 times 4. This is 2 times 2. And then this is 2 times
60.054 is the total.
16.5.
My God. Oh my God.
32.
Yeah, that's about what I'm getting to.
And then this is 4.032. And then this is 24.02.
Change.
Yeah, nice job, guys. I'm pretty sure you have the right answer.
And that's all equal.
Oops, I was muted. I was asking, did we make any progress or are we stuck? How's it going?
I got like 60.02.
Yeah, that's pretty much right. Depending on what periodic table you use, it'll like fluctuate in the hundredths and thousandths place a little bit, but nice job. That's basically right.
Recording in progress.
Yeah, it's telling me that every time too.
What? That is the correct. I have a question. For the periodic table, will metal become gas?
Basically, you will never encounter a metal that's a gas. That's like within the realm of like high school and even to a certain extent college chemistry. Like you just won't encounter that. But there is like some, I guess, far out research that does deal with that kind of stuff. So it exists, but you'll never see it.
Oh, how can it become gas? Because metal, it can only become like a sleepy liquid at most.
Yeah, if you're thinking of like mercury or like gallium, yeah.
No, I mean
It's
not
hard to
mercury.
imagine.
I mean like you heat up, like you ignite a fire and then you melt the metal with the fire.
Yeah,
Any
yeah,
metal,
I know what you
like
mean.
steel.
Mm-hmm.
But then we eventually turn to gas. It would make the heat get higher and higher and higher.
Yeah, theoretically, but like we don't have the methods to get that hot usually, you know?
Yeah, the only way to get it super close to the sun. What if you get it super close to the sun?
You can find out yourself when you become an astronaut. How about that?
Probably not.
All right.
Probably may want to be a teacher, for maybe like science, those stuff.
That's cool.
Well,
All
at least
right.
I want to see if is it possible.
So if you were looking at the slides, you can see like we had a couple left. So it's 1, 2, 3 at the end. So what we can do, since we're running out of time here, you can try these on your own as practice, right? So practice with stoichiometry, harder stoichiometry. I said harder, but it's not really that hard. And then we have this last one, which is called a limiting reactant problem. So you can try those on your own. We might send out like a Google form on the Google Classroom just to like collect your answers if you had any. Don't worry if you didn't, because like obviously we didn't cover how to do these. And then at the beginning of the next class, I'll just review and cover how to do each type because they're like pretty common question types. But for today, we've covered all the content. So if you have any questions, like feel free to like unmute and say them or like just use the chat, I guess. But we're done with the content for today. So I'll stop recording here.